comment on that picture. I don't look like that in real life. I only wore the suit that one time, I swear. So yeah, today I'm going to be talking about Avalanche HyperSDK and how people are going to go about building purpose-built chains on Avalanche with it. So first of all, what is the HyperSDK? The HyperSDK to me starts off as a high-performance execution engine more than anything else. This is, we've spent years working on the Avalanche primary network and decided these are a good set of trade-offs to make in order to give people performance out of the box as easily as possible. Ideally, on top of this, it's tuning it to your performance requirements and starting to make it so that you can swap out different components to match your use case. Whether that's pessimistic concurrency control versus optimistic, swapping in and out the database implementation, etc. Defining your application logic.
The interpreters need you to slow down.
Oh, okay. Awesome. Defining your application logic as easily as possible. This means that if you are building a purpose-built chain, ideally you should only have to define your application logic. And rather than having to define the P2P network, consensus, storage, all of these other components that go into building a blockchain, if you want to build a high-performance blockchain, all that you should really need to do is define your application logic, and all of these other components should come directly out of the box. And ideally, expose an interface to make it as easy as possible to get the most out of them for your use case. Another big component of this in the HyperSDK is to support multidimensional fees. So for high-performance execution, the pipeline that we have today starts out with distributing the data via decoupled state machine replication, agree on the data via consensus, executing the data, which means parallelizing everything with batch signature verification, pessimistic concurrency control, and deciding what fits your use case the best. And then finally, storing the data, writing it to whatever store makes the most sense. For now, that is the Merkle DB and Avalanche Go, which provides Merkleization and is aiming to provide high performance as well. So this is our approach for HyperSDK scaling and scaling on Avalanche. A lot of other chains have gone the direction of what I would call YOLO scaling. And a different presentation, which was not public, I had a quote from another team that's been removed. But YOLO scaling is saying that we haven't made performance optimizations yet, but we're going to figure it out down the line. And I have a huge amount of respect for this, as move fast and break things and fix them over time. For us, we've tried to take a more conservative approach and are going with what I would call data-driven scaling. And the metric that we care about for this is, what is the worst case verification latency or execution latency of a block? And this matters a lot because when you're executing a blockchain system, every time you execute a block, if that happens to have a high degree of variability, if it happens that most blocks might take 100 milliseconds, 500 milliseconds to execute, but one has a huge degree of variability and ends up taking 10 or 20 seconds, then your system will be extremely unstable and run into serious issues. So blockchain systems are all about constraining your worst case. This has been the case for Ethereum for a long time, Bitcoin for a long time, and Ethereum, whenever they had an opcode that was mispriced, this is a DOS vector. And so the way that we generally think about this is, if there is some case that can cause your worst case verification latency to rise far above what you expect, that ends up being a DOS vector. And so very concretely, what we want to do with the HyperSDK is make it as easy as possible for you to manage that case with your specific workload. So that is two metrics that we're going to care about here are the worst case block verification latency and how much that number changes over the course of a year. And this is where the topic of state growth comes into play, a topic that's been very popular and talked about in the EVM community for a long time, because over time you have to continue to write this state to disk. And in both the Merkle tree and database systems today, that results in 2 levels of write amplification. So what you can end up with is, if your state size is growing drastically over the course of a year, you're actually going to see that worst case verification latency take longer and longer. What we see with the EVM right now is that about 80% of block verification time takes place during state access. And both of these, as the state gets larger, both the Merkle tree operations as well as the database operations suffer from write amplification. So we want to make sure to limit this case as well. Now, this is my wonderful graphic about multidimensional fees. I love making little analogies. In this case, imagine that you're selling different fruits. Oranges cost $3.53, pineapples cost $3.65, and bananas cost 86 cents. In most blockchains today, there are single dimensional fees, which means that whatever resources that you're paying for, you pay a single price per unit of that resource. This means that we pay a fixed amount per unit of bandwidth, storage, write access CPU, And in multidimensional fees, the idea is that we treat each of these as orthogonal resources with their own dynamic fee markets. So imagine, you see the fruits before you today, and that's a crazy phrase. You see the fruits before you today, and someone is saying that you're forced to sell bananas for $3.65, even though you'd be willing to sell them for 86 cents. This is effectively what happens when you have a single dimensional market for orthogonal resources. With that, what you have is, let's say in the EVM, we are limiting our worst case, which might be a large number of random writes within a single block. And we do actually see this become popular over time. For example, minting a large number of NFTs generally ends up as being a case of this worst case. And if you're trying to limit this amount with a fixed price per individual write operation, you might end up having to raise the price for that resource and then having leftover bananas or bandwidth or CPU that you're not selling as much of as you might want. And this means that there's a lot left on the table, a lot of fruit, a lot of bananas. And so what we try to do with multidimensional fees is to accurately price each of those resources and then enable applications to match the application and hardware to each of those resources. If they want to keep their entire state in memory, they can make it so that the state will never grow past a certain bound. If they want to run with very, very high bandwidth requirements on their machines, they can configure the fees to match that case. So I have two versions here of what it takes to build with the HyperSDK. I have the easy version, which is the simplest possible case of building on the HyperSDK and defining your application, and then I have the hard version later on. So the easy version is that we've broken this down into a simple action interface and done literally all of the other possible work for you. I should say that this API is not 100% stable. This is actually a very, very early presentation of the HyperSDK, and we're looking to stabilize our API by the end of this year. With that, all that you get as an action developer is this state interface where you have the ability to access an arbitrary key value store, retrieve values, insert or remove values, and then you end up implementing your actions directly on top of this. So this is a level lower than building a smart contract with Solidity in the EVM. And instead, you actually define each of the low-level state accessors directly. So you can see in this example, this is building what I call a very, very simple and naive name service. And all that we do here is we map an individual address to an arbitrary name. So what we do here is we create a name prefix to store all of the names under, and then we copy the address into the latter half of the byte array. In order to set the name, we add this helper function. In order to insert that into the state, in order to retrieve it, we simply retrieve it. So this is a very simple, slightly more than a hello world example. Next, all that you actually have to do is define how you retrieve the state keys for your transaction or for the action and what to do in order to execute it. So with state keys, this is what we talked about with pessimistic concurrency control and dynamic prefetching. So as you implement the state keys function, this tells the transaction and the HyperSDK exactly what state keys you're going to touch throughout the transaction's execution. And this enables us to prefetch all of the state keys in advance, fully in parallel with all of the other transaction state keys. And it also enables us to perform concurrency control for you and execute with pessimistic concurrency control. So this actually specifies the exact permissions required in order to perform the operation. So you specify state read, write, allocate as well, in order to say that we can actually differentiate between read and write operations and get you the most concurrency possible. Next, all that you have to do is implement this execute function. With this execute function, you use the storage helpers directly, provide whatever additional verification that you want to the action struct itself, and perform the operation on state. What we do with this approach is we actually have these get name and set name structs that are defined in your application. And we use the Avalanche Go codec and our own ABI definition so that we can actually do all of the work for you. So you don't have to worry about serializing this, wrapping it into a transaction, building an Explorer front end. We actually have an ABI for both the inputs, the actions themselves, as well as the outputs. So if you've ever implemented a Solidity smart contract, this corresponds directly to an individual function on a Solidity smart contract. So in this case, get name is a read function. And if you wanted to access this via an API call, the corollary would be eth_call in the EVM. And in this case, we have a simulate action API that enables you to say, okay, here's the action I want to simulate, and here's how I can read directly from the state. In the same way with set name, this is the actual action that would be included in a transaction on chain. And this is how you would actually say, okay, I want to perform this action, include in a transaction, and have it be executed. Now, that's all that it takes in order to build. Fast talker. So that's all that it takes to build a very, very simple application on the HyperSDK. The application, you only really have to worry about your application logic, and we've already made a lot of decisions in the background to make it as performant as possible. So this is what I call building with the HyperSDK on easy mode. Building with the HyperSDK on hard mode is sort of what the future looks like, in my opinion. And this is that for purpose-built chains, you actually might want to care about a lot of the different decisions under the hood and play around with a lot of the different toggles between pessimistic and optimistic concurrency, exactly what the multidimensional fees ought to be, what database system that you might be doing, in order to, just like you'd be building with the Web 2 application, get the full level of configurability and choose your entire stack with the HyperSDK as a sort of skeleton or framework to fit that into. I do it with all these options out of the box. So on hard mode, this means becoming a protocol dev. It means understanding the layer underneath. So if you are building a Web 2 application, to use a database well, you have to understand its internals. You have to understand that you want to perform write sequentially, how to perform read operations effectively. And in order to start out, what you probably do is decide your data layout, optimize your read and write workload for it, build your application on top of that, and then continue to iterate. And if you're building a Web 2 application, there is no way that you're going to iterate only on the front end part of that application. You're going to continue to iterate on the full stack. And so I think that's what we're going to see, hopefully with developers that are using the HyperSDK, is that you continue to figure out what actually works best for your use case. So if you are building a purpose-built chain, you're going to be willing to sub out these different components, swap between them, and see what works best for your use case. So the new layer underneath for devs that are building on the HyperSDK is this execution pipeline that in order to use effectively, you want to know exactly how it works, the exact details and how your application interacts with it. You want to know exactly what your current state size is, exactly what is contained in your current state, and what you actually need about that information. The most expensive part in the EVM is maintaining a large current state size. And so whatever you can remove from that over time, whether it's via expiry or limiting the state size that you'll ever reach, this is a very, very important detail to your application. And as you switch from being an application developer only on the EVM to being a protocol developer building a purpose-built chain, these are the things that if you want to be a top-of-the-line developer, you ought to start to care about. In the EVM world, I think what this looks like for Solidity developers is that they start to care about gas costs. They start to realize that if we write in assembly this one particular function or we pre-generate this function selector, we might actually get better performance. A lot of the times those things don't actually match up with what leads to the best performance on chain, but that's what people end up optimizing for. In this new world of building a purpose-built chain, you'll want to start to worry about this layer underneath and exactly what your requirements for it are. So that means understanding the current state, exactly what you need about indexing the historical state, and exactly what you need in terms of what data actually needs to be verifiable. All of these things come with trade-offs, and the more that you can deeply understand your application and exactly what you need from it, the more you can get rid of the things that you don't and only include the ones that you do. So quick interlude on state. I'm going to see if I'm able to share my screen or share this as an example. I really like this visualization from Paradigm. So as an example of why this matters, this is a visualization of the entire Ethereum state space. Yeah. This is about 250 gigabytes, and this means that for Ethereum, if they want to run on commodity hardware, which is their stated goal, they need to keep a large amount of this on disk. They have to worry about the worst case verification latency when they're writing all of this to disk and might have to perform a large number of reads. But I want to zoom in here on a couple of different applications to give you an idea of actually how easy it might be able to scale a purpose-built application. So Uniswap, as an example, is 2.8 gigabytes of total state in Ethereum. And this means that if you wanted to keep that entire state in memory, it would only take about 2.8 gigabytes. So and this is a decentralized exchange, a lot of the problems that you have when building on Ethereum or building as a protocol developer become very, very difficult when you try to do it in the general purpose sense, try to handle every possible thing. And those problems, the issues that you're going to run into in scaling, becomes totally different when you're building a purpose-built application for one particular use case. You know, you have Uniswap takes up only 2.8 gigabytes, accounts take up about 35 gigabytes, and you can even look at these individual games, and the sum of all games indexed in this is less than 5 gigabytes. Everybody's laptop in this room probably has enough memory to handle all of those. So if you did want to run on commodity hardware and you wanted to run a purpose-built chain, you actually probably could for many of these cases. So this, I think, is one of the really nice trade-offs that you get out of building a purpose-built chain, is you can actually think about what is the size of the state that I'm actually going to need and optimize for that case. If you do keep everything in memory, in order to optimize for throughput, what you end up starting to care about instead is what is the sustained write rate of my application? What is the maximum number of new entries that I might have to write to state? This is the only storage requirement that you're really going to end up caring about. Reads aren't going to matter as much because you're going to have the whole state in memory. And you can very easily limit the number of writes, either new allocations or writes to existing state, by configuring the multidimensional fees. So you can very easily limit what your worst case is, even in this case. Yeah. Go back to slideshow. So with that, we have a hackathon this weekend. I'd love to see any of you guys there if you're building any type of application. I think that there's many applications that can be built on top of general purpose chains and might even be better to build there. But if you are interested in building a purpose-built chain, proof of concept on the HyperSDK, I'll be there all weekend this weekend, and would love to work directly with any of you guys on listening to exactly what you guys want to build, exactly what your requirements are, stepping through them, walking through them with you, and seeing what might make the most sense as we continue to make changes and iterating on the HyperSDK design. So yeah, thank you all for coming, and I hope to see a lot of you guys at the hackathon.
Awesome.
Can I ask you one question?
Yeah.
If you had to recommend some study material for HyperSDK side. Hello, amazing presentation. Really enjoyed. If you had to recommend me some study material for HyperSDK and optimizing gas, what would you recommend me besides the ABAX Academy?
Where's Rudy? Oh. I would recommend talking to him or me and asking all of the questions. And also, for me as a developer, I never learn anything better than by just doing it. So I'd recommend building something, trying it out.
Just not to take your time so much, I would.
No, I'll do it with you. We'll spend the time this weekend.
Okay,
More than
I
happy
really
to.
appreciate it.
Yeah.
Amazing. I really enjoy.
Yeah, we'll both be there this weekend to spend time with anybody that wants to learn about it. And Rodrigo's also written some fantastic documentation that we're already getting great feedback on too. So actually, if you go to the HyperSDK, there's a docs subdirectory that has some great explanation material as well.
Okay.
I
really appreciate it.
Awesome.
Thank you.
And if you are a developer and interested in working on it, we have a few issues labeled good first issues too. If you'd be interested in getting involved, we'd love to help out.
It's like probably my younger sister, not me, but like.
Either way.
I really enjoyed it. Thank you.
Does AWM work natively with HyperSDK?
Yeah, that's a great question. So there was an AWM integration previously, and it was removed. We're certainly going to add it back.
Okay.
Composability is very important. It's much more valuable to build a purpose-built chain that has interoperability with an existing ecosystem than to build one entirely on an island. So we're certainly going to add it back, yeah.
Thank you.
Sure.
Thank you. I know it might be early for this question, but like on the test bench, has anyone ever upgraded an EVM network upgrade to a Hyper VM, to a different VM?
You mean switch from one to the other?
Exactly. How would that work in a production environment?
Do you mean switching from an application that was on the EVM to running on the HyperSDK, or?
A network upgrade from an EVM chain to maybe a custom VM.
So are you talking about migrating the whole state or just switching the application? Yeah, so certainly nobody has ever, nobody's launched an application in production, so it'd be hard to do a production upgrade in the first place. The only thing that we've done on this is we had one of the engineers on our EVM team did build a proof of concept for what it looks like to run the EVM directly on the HyperSDK. This was building the EVM itself as an action on the HyperSDK, so that if you wanted to, you could use Solidity smart contracts out of the box. This does come, though, with a lot of trade-offs, because, not maybe trade-offs, but differences in what you'd expect using the EVM, because you are using HyperSDK transactions out of the box instead. So that EVM, or calling an EVM smart contract, ends up being an action within a HyperSDK transaction. as opposed to using Foundry to issue a normal Ethereum transaction. So we're building all of the tools around this to have an Explorer, API service, wallet support, everything, but all of these things would look a little bit different.
Thank you.
Sure. To answer a little bit more of what I think you were trying to ask, it would be probably difficult to migrate the actual state of an application from the EVM to a HyperSDK application. A much easier path would probably be to deploy a new instance of the application and have people move over their use cases. So, like this is what Uniswap typically does when they deploy a new version. So they don't actually upgrade from one to the other, but they just say, here's the new version, you can start to use this. And oftentimes that just means starting to move incentive programs around to the new one so that people start to use the new version.
We still have a little bit of time left. Does anyone have any other questions to ask? Oh,
When do you think HyperSDK will be ready for production scale applications?
That's a great question. Rodrigo, what do you think? No, we haven't announced any timelines yet because the API is not stable. Yeah, so we don't have any timelines yet, and that's very much a policy. We don't want to give people a timeline and say, this is actually going to change completely. We're going to start giving timelines as we get to a point where we have a lot more confidence in exactly when it's going to come out.
Yeah, do you have any test framework for benchmarking suits for HyperSDK chains?
Yeah, we have a very terrible testing benchmark that I wrote that I don't recommend using. We're rewriting it right now. The team, the rest of the HyperSDK team is actually having a meeting right now going over exactly what we want to do in order to make it as easy as possible. What we do have right now is, as I said, this terrible testing framework that I wrote to sort of migrate the existing tests over. And that is, we have this framework where you basically have a transaction generator and you just issue a sequence of transactions. The reason we implemented it this way is that we wanted to support testing the HyperSDK itself, where it wanted to generate a sequence of transactions or a sequence of blocks and test different things that might happen, like triggering different phases of bootstrapping or having a chain of processing blocks that we accept one after the other, or conflicting blocks that we accept one and reject the other. And for this, we don't need to know what is actually in the transactions. So we added this interface that it could be shared between different VM implementations, and they would get that testing out of the box. The problem with this is that it's not really the typical style of writing tests that you would be used to. It's this weird transaction generator thing, and what you probably want to do is write step 1, check that there's no errors, check that all the conditions you expect are met. Step 2, instead of that, this would be one transaction generator that has to handle its own stepping between steps. So there is a GitHub issue, and I think the team is making some comments on it right now to figure out the best path. But we're going to support that procedural framework, most likely.
any last questions? Alrighty, thank you, Aaron.
Thanks.